The skeletal system has long been viewed through a mechanical lens, bones as load-bearing structures that grow stronger with use and deteriorate with age. Osteoporosis, the most common bone disease in older adults, is traditionally explained by an imbalance between bone resorption by osteoclasts and bone formation by osteoblasts. But this perspective is evolving. New research suggests that bone is not just passively eroded by aging, but actively disrupted by biological processes rooted in cellular dysfunction, particularly cellular senescence. These so-called zombie cells, long known for their role in other age-related diseases, are now emerging as potential culprits in skeletal deterioration. Their presence in the bone microenvironment may help explain not just why bones lose mass with age, but why they become more fragile, inflamed, and resistant to repair. Senescent cells accumulate in many tissues as we age, including bone marrow, where hematopoietic and mesenchymal stem cells, MSCs, reside. MSCs are crucial for bone regeneration. They give rise to osteoblasts, which form new bone. But as these progenitor cells become senescent, they lose their capacity to differentiate, proliferate, and function. Worse, they don't go quietly. Instead, senescent cells secrete a toxic mix of inflammatory cytokines, matrix-degrading enzymes, and reactive oxygen species, known as the senescence-associated secretory phenotype, SASP. This inflammatory cocktail promotes bone resorption and inhibits formation, a perfect biochemical storm for osteoporosis. Studies have shown that in aged mice, senescent cells accumulate in the bone microenvironment, especially in osteocytes, long-lived cells embedded in bone matrix, and bone marrow stromal cells. These cells show markers like P16-INK4A, P21, and elevated SS-galactosidase activity, hallmarks of senescence. When researchers use genetic or pharmacological tools to eliminate these cells, bone density improves, microarchitectural integrity is restored, and fracture risk is reduced, even in animals already showing signs of bone loss. These findings strongly suggest that senescence is not merely a marker of aging bones, but a mechanistic driver of their failure. Importantly, this effect is not limited to the structural aspects of bone. The SESB also interferes with the bone immune axis, skewing immune cell profiles in a way that sustains chronic inflammation, a process sometimes referred to as inflammaging. Chronic low-grade inflammation further stimulates osteoclast activity, tipping the balance toward bone resorption. In women, this effect may be particularly pronounced post-menopause, when the protective anti-inflammatory effects of estrogen wane and inflammatory signaling surges. Senescent cells are known to expand rapidly during this period, and their removal in animal models has been shown to reduce the severity of estrogen deficiency, induced bone loss. The implications for human health are significant. Current osteoporosis treatments, such as bisphosphonates, denosumab, or anabolic agents like teriparatide, primarily address the downstream effects of bone loss. They can increase bone mineral density and reduce fracture risk, but they do not correct the underlying cellular environment that allows bone degradation to persist. Senolytics, by contrast, offer the possibility of modifying the terrain, restoring a more youthful, regenerative bone microenvironment that supports both structural integrity and metabolic function. Preclinical studies using senolytics like dasatinib and quercetin, D plus Q, have already demonstrated positive effects on skeletal health in aging mice. Treated animals show not only improved bone mass, but also better coordination between bone formation and resorption, suggesting a restored homeostatic balance. Natural compounds such as physatin, found in strawberries and other fruits, are also being explored as bone-friendly senolytics, given their relatively low toxicity and broad anti-inflammatory effects. Still, the translation of these findings to humans is in its infancy. Clinical trials are beginning to evaluate the systemic effects of senolytics in older adults, particularly regarding physical function and inflammatory markers, but their specific impact on bone is not yet well characterized in humans. Questions remain about optimal dosing, timing, and potential off-target effects, especially given the need to preserve some forms of cellular senescence that serve protective or regenerative roles. Nevertheless, the concept is deeply promising. If future therapies can safely clear senescent cells from the bone marrow and osteogenic niche, or suppress their inflammatory signals with xenomorphics, we could offer aging populations a new kind of osteoporosis treatment, one that not only halts the decline but rejuvenates the system itself. This would be a shift from reactive symptom management to proactive cellular repair. In the broader context of longevity and musculoskeletal resilience, targeting senescence could also complement lifestyle interventions like resistance training and nutrient optimization, both of which are known to stimulate osteogenesis and modulate inflammation. The skeleton, once thought to passively decline with age, might instead be viewed as a living, dynamic tissue with the capacity for renewal, provided we remove the biological roadblocks that stand in its way. By illuminating the role of senescent cells in bone loss, we are no longer limited to patching structural holes in an aging framework. We are learning how to revive the regenerative processes that kept us upright and mobile in youth, opening the door to a future where fractures and frailty are not an inevitable price of growing old, but a preventable consequence of unaddressed cellular dysfunction.